Hi folks, Mr. S here. This lesson is on energetics or thermochemistry, which is the study of energy changes in chemical reactions. Some of the terms you'll come across here are your chemical system, which is referring to your reactants and your products, surroundings, which is basically everything else. If the reaction is done in a test tube, it would be test tube. If there is water in the surroundings, then of course water would be part of the surroundings. Heat is the transfer of energy from hot to cold objects. Enthalpy, symbol H, is the total heat content of a substance. So if you can imagine all the energies added up, and then change in heat would be the change in heat of that particular substance as the reaction happens. You will also come across types of systems here. We're basically dealing with experimental methods. So if you're doing an experiment, typically you'll see that when we're doing experiments, we would be using what's called an isolated system. An isolated system prevents the loss of energy, and it also prevents the loss of matter. So if the reaction produced a gas or whatever, there'll be nothing lost. Here, obviously, you would lose both matter and energy. And here, you would only be losing energy. So like I said, when we are doing reactions that involve thermochemistry, we would be using an isolated system. Reactions can be exothermic or endothermic. Exothermic means that they lose heat to the surroundings. Endothermic means that they absorb heat. So if you take a look at an exothermic reaction here, you can see that the reaction is shown as red, which means that it is hot, it has lots of heat, and it loses that heat as the reaction goes, right? As the reactants go on and form products, the reaction is losing heat. And you see that the surroundings, which is shown by this thermometer here, it starts to heat up because that heat from the reaction is going in to heat the surroundings. Typically, a thermometer, like I said, will tell you, and the the temperature will go up. So here your surroundings are gaining energy and your chemicals are losing energy. On the other side, when you see that my chemical system is colder, here heat has to come from outside to get this reaction going. This is endothermic. Endo means entering. So in this case, heat has to enter. And you can see here my temperatures will actually, my surroundings will lose heat because the temperature of the surroundings will go down. An example of this would be an ice pack. When you get injured and you put an ice pack on your leg, for example, what will happen is that ice pack feels cold because it's sucking up the heat from your body. So it's using the energy of the surroundings, and that's why your leg feels cold, but that allows the reaction inside that packet to occur. So two terms here, the energy of the surroundings. So in this case, my surroundings is gaining energy. In this case, my surroundings is losing energy. We represent that by the letter Q, and you will see that. And then the energy of my chemical system, in this case, it's losing energy. In this case, it's gaining energy, is shown by delta H. So if the chemical system is losing energy, delta H is negative, and if the chemical system is gaining energy, gaining heat, the change is positive. Essentially, we're saying the change in heat here is negative. As my reactants go to form products, I am actually losing heat here, and as my reactants go to products here, I'm actually gaining heat because that heat is coming from outside. So delta H refers to the energy of your chemical system, or the change in the heat of your chemical system, and Q is the change in the heat of your surroundings. What is the relation between enthalpy change and Q? Well, if we do this in an isolated system that I showed you earlier, and all the heat in this exothermic reaction goes to the surroundings, and I can trap all of that heat, and I can find out exactly how much heat was gained by my surroundings, which is my Q, I can now safely assume that Q is equal to delta H. The only difference here would be their signs. My surroundings here will gain energy, so it'll be positive, and my delta H will be negative because the delta H is referring to the enthalpy change, or the heat change of my chemical system. So if your delta H is positive, that means you're dealing with an endothermic reaction, your surroundings will lose energy. And if your delta H is negative, which means we're dealing with an exothermic reaction, your surroundings will gain energy. We can show exothermic endothermic reactions using an enthalpy diagram. In this case, this is for an exothermic reaction. An enthalpy diagram basically is a graph that shows the relative enthalpies of your reactants versus products. Typically, there's no numbers shown here. All it's saying is, okay, here's my reactants, here's my products. You can see my reactants so the enthalpy of my reactants is greater than the enthalpy of my products. In other words, my reactants have more heat than my products. And as the reactants go to form low energy products, this difference in energy obviously gets released to the surroundings. So you can see here that as I go from reactants to products, my chemicals are losing heat, and that heat is going to the surroundings. That's the delta H, and delta H is negative. If I were to just quickly put numbers here, if I made this 5 and if I made this 15, you can see delta H is enthalpy of products minus enthalpy of reactants. It'll be 5 minus 15, which is negative 10. So your delta H is negative. If the delta H is negative, then you're dealing with an exothermic reaction. For an endothermic reaction here, you have lower enthalpy reactants going into higher enthalpy products. This is a process that does not happen on its own. It tends to be non-spontaneous, so we have to put energy from outside. Hence the term endothermic, which means that heat has to enter my system. Here, my chemicals are actually gaining heat because I'm going from low energy reactants to high energy products, which means my enthalpy change here will be positive. Just a quick note here. In this section here is that if you have low enthalpy, that means that you're more stable energetically, and then typically you also have stronger bonds. When we're doing kinetics, you will also learn about enthalpy profile diagram, which is just a modified enthalpy diagram. You can see the enthalpy of reactants here. This is the enthalpy of your products here. However, we have this bump now. This is called an enthalpy profile diagram. So what it's basically saying is that unlike the enthalpy diagram, the reactants are not just going and forming products directly. There is actually a change in their potential energy. You can see for an exothermic reaction here, the bump, the distance between the reactants and the bump is not as high as it is here. You will learn about a concept called activation energy, which is the energy that's required to get the reactants to the top of this hill. This is also known as transition state theory. We're going to talk about this in kinetics. All right, once we've determined the enthalpy change for a reaction, then we can put it beside the equation, and at that point we call it thermochemical equation. In this case, I can tell that this is an endothermic reaction because there's a positive number here, and the enthalpy change here is negative, so I know that this is exothermic. Now, this is quite handy for me. Once I know the enthalpy change for this reaction, I can now say, okay, what if I wanted to make 4 moles? So I now know how much energy I will need or how much energy is released in the case of the second one. So what if I wanted to make 4 moles of nitrogen monoxide in a reaction? Obviously, I would need more nitrogen and oxygen. However, it tells me now that I would need 2 times this amount, right, to make 4 moles of that. What if I only wanted to make 1 mole of it? Well, it would tell me that I would need 90 kilojoules of that. Same thing with question number 2. Now, here you could be asked some questions here. So here's some examples of questions that you could be asked. So what is the enthalpy change per mole of nitrogen monoxide? So this, keep in mind that this is written as kilojoules, not as kilojoules per mole. So if I said, okay, how much energy is released per mole of nitrogen monoxide? Well, you know that, sorry, in this case, it's not released, it's absorbed. In this case, 180 kilojoules is absorbed for 2 moles of nitrogen monoxide. So for 1 mole of nitrogen monoxide, like I said earlier, I would just take that number, 180, and I'll divide it by 2, and that's going to give me 90 kilojoules. You could also be asked a question like this. What if you were reacting 64 grams of oxygen? So if I had 64 grams of oxygen, how much energy would be absorbed? I know that when 1 mole of oxygen reacts, this is how much energy is absorbed. So what I would have to do is I'd have to convert that to mole, which turns out to be 2 mole, because the molar mass of oxygen gas is 32. So if you divide this by 32, I get 2 mole. Well, I can now set up a quick ratio here. 1 mole will require 180 kilojoules, so 2 moles will require twice that amount. Sometimes you'll see a little theta sign here beside the enthalpy change. That just means that it's been determined under standard conditions, which is 1 molar solution. This is the concentration, 100 kilopascals pressure, and 298 kelvins. Other times you might see something like this is for a neutralization reaction. You might see, if this was for a combustion reaction, you might see COMB, etc. No need to worry about that. So now we're coming to the main part of thermochemistry, which is basically determining or calculating enthalpy change. Remember, enthalpy change is the change in the enthalpy or change in heat of my reaction. We can do this experimentally using something called calorimetry, or we can use non-experimental methods. In this case, obviously experiments were involved to get the data, but we will use data and these 3 specific methods here to calculate enthalpy change for a reaction. Let's take a look at calorimetry. I've listed 3 types of calorimeters here. We have a simple coffee cup calorimeter, a flame calorimeter, and a bomb calorimeter. So number 2 and 3 are used for reactions that produce fire. So for combustion reactions, Number one, the simple coffee cup one will be used for, reactions involving solutions, for example. So if I was doing, let's say, an acid-base reaction, so here I would mix these two together and there'll be a small temperature change and I can measure the temperature change here. One thing you notice with all calorimeters is that water is a main part of it. Here I have water in a container. Here in this particular case here, I'm trying to find how much energy there is in a peanut. Here, for example, you can use a bomb calorimeter to find out how much energy there is in food. Let's say, for example, if you were to find the calories of Big Mac, this is essentially what you would be doing. You would take the Big Mac and you burn it as the heat is released into the water. Then you will see that in all forms of calorimetry, we take the heat that's gained by the water. We use a thermometer. So we're going to find the water here as part of my surroundings. So I'm going to calculate Q, which is how much energy the water gains. And then I'm going to say, okay, that energy that was gained by the water came from my reaction. So my delta H here would be negative. Just a quick note here, when we are doing coffee cup here, the water is actually part of your reaction. So it's mixed in with your chemicals. However, the water is still your surroundings because these are both solutions. So they had to be dissolved in water to get this reaction going. Now, when we are doing calorimetry, you'll see that we do the reaction, we transfer the heat to a known mass of water, a known amount of water. So we need to know how much water we have. In the case of a coffee cup, if I'm mixing 50 of this and 50 ml of this, for example, then my total volume here is going to be a 100 ml. And typically we assume all of that to be water. Here, like I said, once again, I would need to know how much water I have in here. And then I would need to know how much water I have in here as well. So in all forms of calorimetry, we do our reaction. We transfer the heat from the reaction to a known mass of water, and we do a bunch of calculations. So here are our basic steps or basic premise. Energy of an exothermic reaction, again, we're focusing on exothermic reactions, is transferred to a known volume or mass of water, and the energy gained by the water is calculated. How? Well, we're going to see this formula very quickly on the next page. And then we're going to assume here that the energy gained by the water was equal to the energy lost by my reaction, because all the energy here that came from my, let's say, burning that piece of Big Mac here went into this. Now, a bomb calorimeter is a perfectly isolated system. Again, I'm simplifying these calculations for you right now. So this would be the best system to use if I wanted to find how much energy there was in a Big Mac. This system that's set up here is not very efficient because heat could also be lost here. We want all the heat from here to be transferred to water. Okay, so let's take a look at how we calculate how much energy is gained by my surroundings, in this case, water. So you'll need three things. You'll need the mass, something called specific heat capacity, and the change in temperature. This you can measure using a thermometer. Mass for water, 1 ml of water has a mass of 1 gram, because density of water is 1 gram per mil. And then C is specific heat capacity, which is defined as how much heat is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Essentially, what that means is if I take a look at the number for water, and let's say if I take a look at the number for gold, if I were to heat gold and water for the same amount of time, gold will heat up much quicker than water. That's what that number means. So the higher the number, that means that the lower the temperature change. This is the reason why you can walk on a beach on a hot day and the sand feels hot, but the water feels cold. Once you have all of these numbers in here, I would suggest you memorize the number for water. It's 4.18 or 4.184. Once you plug all those numbers, you're going to calculate Q, which is, for an exothermic reaction, is going to be a positive number. That is the amount of energy that is gained by your surroundings. Like I said, in calorimetry, our surroundings is water. So you just found out how much energy water gained. Well, where did the energy come from? It came from my reaction. So, step 2, energy gained by the water is equal to energy lost by the reaction, and then we can calculate the enthalpy change. So once I have Q, how do I go to enthalpy change? Well, delta H is basically equal to Q, but remember, in this case, Q is typically in joules. When you solve Q equals MC delta T, so we're going to convert this to kilojoules. So delta H, if this is positive, my delta H is going to be negative. Delta H is in kilojoules. Now you can also express that in kilojoules per mole. So how do we do that? Well, I would need to have some way of finding mole. If they've given me the mass of something, you can also express it as kilojoules per gram. If you're finding the amount of energy in let's say, in a chip or something, you can find its mass, so on and so forth. Non-experimental ways. So there's 3 here. We're just going to quickly go through them. We can use average bond enthalpies. something called Hess's law of heat summation, and then enthalpies of formation. I think in my slides, this is number 2 and this is number 3. So this is number 2 here, and this is number 3, just so we don't get confused. Let's take a look at average bond enthalpies. The energy required to break 1 mole of a bond averaged over different molecules. What that basically means is that here's CH bond here. How much energy do I need to break 1 mole of that bond? Well, it's 412 kilojoules per mole. And this is averaged over different molecules. Basically, what they're saying is if I'm looking at, let's say, a CH bond in methane versus a CH bond in propane. Now, you don't know what these things are just yet, but you're going to learn about them in organic chemistry. What they're saying is that because of the environment, this CH bond and that CH bond might have slightly different values. So what we do is we average them and then we list it on this table. So one of the things you'll notice here is that when I'm comparing a carbon-carbon single bond, a double bond, and then a triple bond, you can see that the numbers is 348, 612, and 837. Obviously, it tells you that a triple bond requires more energy to break. Keep in mind that bond breaking is endothermic, which basically means that it needs energy. Which makes sense, right? Because if you're trying to break the bond between two substances, and bond formation is exothermic, which basically means that it releases heat or releases energy. So, just a quick note here. This amount of energy is required to break 1 mole of CH bonds. That is the amount of energy also released when 1 mole of CH bond forms. That's what this is telling you. All right, how do we use average bond enthalpies to determine enthalpy change for a reaction? Typically, you'll be given a question like this. In this case, C2H4 reacts with oxygen gas to produce carbon dioxide and water. First thing you want to make sure is that the equation is balanced. In this case, my equation is already balanced. Next thing you do is you draw these molecules out to identify the types of bonds in each. So this guy looks like that. That's the Lewis structure for it. Oxygen has double bonds, and there's 3 of them. Excuse me. There's 2 carbon dioxide, so here's the carbon dioxide. We learned how to do these structures before, and water is like that. I have 2 water molecules. So all you have to do now is this. You're going to apply this formula. Sum of bonds broken, which is the reactants, minus the sum of the bonds formed. So in this case, the bonds that are broken are your reactant bonds. In any reaction, reactant bonds are broken and product bonds are formed. So this side obviously is endothermic. This requires energy, and this side is exothermic. It releases energy. So in this case, I have 4 CH bonds and I have 1 carbon-carbon double bond. And here I have 3 oxygen double bonds, 4 carbon-oxygen double bonds, and I have here 4 OH bonds. What I'm going to do now is I'm going to go to the table and find the value of CH, which is 413. I think it was 412 listed on mine, but it doesn't matter. Use whatever data booklet you have, and that's multiplied by 4. And then I believe in this case we are missing the carbon-carbon double bond. Okay, so that's not a very good example. However, so you'd have to do this times 4, and then you would also have to find the enthalpy change for that. So these numbers are not entirely accurate. I think here we're okay, 4 times 805 and 4 times. So this side is okay. This side, we're missing the enthalpy change for that. So you'd have to add that to this number as well. Once you do that, it's just going to be bonds broken minus bonds formed. And in this case, you can see here, they have already put a minus here, and so this would be positive as well. And then you would just put the minus here. So what I'm trying to say is, in this case, in my example, there's a negative here, so don't make that positive. So it's this minus that. Both of these numbers will be positive, essentially, when you're looking at that table. So when you're looking at this table here, all your numbers will be positive. All you have to do is just take the numbers, find the total sum, and then just subtract the whole thing. All right, enthalpy of formation. This is the second method we can use. This is the enthalpy change when 1 mole of a substance is formed from its elements in their standard state. So here we have carbon dioxide, and I'm making 1 mole of it. I need carbon and I need oxygen. This is how carbon and oxygen are found in nature. Carbon is found as a solid. You will see that carbon has different allotropes. So when you are looking at formation equations, which is what I've shown you here, typically you'll see graphite beside carbon because carbon can be found as diamond as well. So graphite is taken to be the standard form. Oxygen is found as O2. And this is what's called a formation equation. So the enthalpy change that is associated with making 1 mole of carbon dioxide is negative 393.5 kilojoules per mole. Here I'm making 1 mole of water. Well, you see it's made of hydrogen gas and oxygen gas. And the reason I put a half here is typically when you're writing formation equations, it's defined for 1 mole. So the enthalpy change for 1 mole for formation of water is negative 248.8. Essentially what that means is if I wanted to make 1 mole of water, this is how much energy is released. If I wanted to make 1 mole of carbon dioxide, this is how much energy is released. We can use these enthalpy changes now and find the enthalpy change for a reaction that involves multiple compounds. So here's an example. The formula here is this. The enthalpy change for this reaction. So I'm looking for the enthalpy change for this reaction. The enthalpy change for this reaction is the sum of the enthalpies of formation of products minus the sum of the enthalpies of formation of my reactants. The N and the M here are saying referring to the number of moles in your balanced equation. Those number of moles come into the equation here. So what do we do? It's products minus reactants. So I'm going to go to my table, and you will have a table in your data booklet. You're going to get the value for carbon dioxide, which is, for carbon dioxide, it is negative 393. For water, remember the water can be liquid or vapor. In this case, liquid water is negative 285. This guy is negative 1260. And one thing you will notice that when you do go to tables to get enthalpy of formation data, there's nothing given for elements that are found in their standard forms, which basically means that that's how we find them in nature. So there was nothing required to make them essentially. All right, so once you do that, you plug all the numbers in and you get your enthalpy change. So enthalpy of formation, you take the formation of the products, add them up, make sure you multiply by the 6 in each case, take the enthalpy of formation of 1 mole of glucose, and then it's going to be products minus reactants. Here is the table of enthalpies of formation. And lastly, we're going to take a look at Hess's law. Now, Hess's law of heat summation, basically states that if I have a reaction, let's say A goes to B, and for whatever reason, I can't find the enthalpy change for this reaction, maybe because the reaction is too slow or too explosive. If I can find simpler reactions, so let's say we have a reaction where A goes to C, C goes to D, and D goes to B, as long as these reactions, so this is reaction 1, reaction 2, reaction 3, as long as those reactions add up to give me my original reaction here, I can take the enthalpy change for the first one, add it to the enthalpy change for the second one, and the third one, and that should equal my enthalpy change. So in other words, delta H equals delta H1 plus delta H2 plus delta H3. How's that happening? Well, if you just quickly list these reactions, let's say A goes to C, C goes to D, and D goes to B, you can see that if I were to cancel like terms like I do in math, these are, you can think of these as equal signs, you can see that if I were to add these 3 reactions, I get A goes to B. Anytime you get to that point where these reactions can be combined to give you the overall reaction, Hess's law states that the enthalpy change for that reaction now equals the sum of the enthalpy changes for these. Now, in this case, my arrows are all nicely pointing up in one direction. So I can go from A all the way to D and then to B. You can see that if I was just doing a little puzzle here. A lot of times what will happen is this reaction here, the arrow might be going the opposite way. If that's the case, you are going to have to flip this because now these arrows are not all pointing in the right direction. So you might have to flip that equation because the arrow is pointing this way. You might have to make it D goes to C. Now you can actually go ahead and find the enthalpy changes. Now, unfortunately, in chemistry, you're not going to be giving these letters. You're going to be given equations like this. This is the equation that I'm interested in. So that would be equivalent to A goes to B. That's called my target equation. And you will be asked to take 1, 2, and 3 and add these 3 equations. And if you can get that target equation, then you can take their enthalpy changes and add them together, and that'll be it. So you'll see that this is the one that actually involves quite a bit of work. So if I were to add these reactions as they are written, I will not get this just by looking at the water. So if I were to add these 3 reactions right now, I would end up with 6 water molecules on the product side. Again, I'm adding the right side and I'm adding the left side. If I add the right side, I'll have 6 waters. There's no water here, which means that I need to manipulate these reactions. What do I mean by manipulating? Well, we already talked about flipping an equation. You can flip, you can multiply an equation, you can divide an equation by a certain number. Whatever you do, remember, however, though, is you will also have to do the same to your enthalpy change. If I were to take this first equation and if I were to flip it, The forward reaction right now, this reaction here is exothermic. If I were to flip this equation, the sign of this enthalpy change will change. If I were to multiply that entire equation by 2, I would also have to multiply this enthalpy change by 2. So where do we start when we're doing this? Well, I'm going to try to identify. The first thing you do is identify. Sometimes, some textbooks, they say, okay, put a circle around this, put a box around this, and put a triangle around this, and see if you can find those reactants and products in these equations. So if I look at C2H4, I can see C2H4 in my reaction 1 here. So C2H4 in my reaction 1, in my original reaction, C2H4 has 1 mole in it, or in front of it, and here the coefficient is also 1. So I'm actually going to keep this equation as it is. I'm not going to flip this equation. Why? Because the C2H4 is present as a reactant here. What about the rest of it? Well, we'll see. Hopefully it'll fall into place. Next, if I take a look at C2H6, C2H6 is in my second equation here. Now you can see here C2H6 is a product, and here it's a reactant. However, I know that the moles are good. So there's 1 mole of this and 1 mole of that. Bottom line is I'm going to have to flip this one. The reason I'm going to have to flip it is because I need C2H6 to be a product, not a reactant. And then lastly, if I took a look at H2, I have 1 mole of H2 here, 1 mole of H2 there, and the H2 is in the correct spot. It's a reactant because it's a reactant in my target equation, so I'm not going to flip that. So if I were to rewrite these equations here, C2H4, I'm not doing anything. The first reaction, I'm just going to write it as it is. I'm leaving the states out for now, but the states are obviously important. You need to be careful. I'm flipping this equation here. So if I flip it, that basically means it's 2CO2 plus 3H2O goes to C2H6 plus 7 over 2 O2. Now, very important for you to remember that because I flipped this now becomes positive. We did not change this one, so that still stays negative. And the last one we said, because the hydrogen is in the correct spot, it's a reactant, there's only 1 mole. I'm not going to touch that either. Now you can see here, so that enthalpy change remains the way it is. Now you can see here that if I were to add these 3 reactions here, I have so if I think of this as the right side of my equation and this whole thing as the left side of my equation, I have 2 waters here, 1 water here, which is 3 waters. That cancels with the 3 waters here. The 2 CO2s are on opposite sides of the equal sign, just like in math. That cancels. 3 O2 plus half O2 is 3.5 O2. 7 divided by 2 is 3.5 O2, which means that this will cancel with those 2 oxygens. What I end up with is C2H4 plus H2 goes to C2H6. And now you can see that this equation is actually the same as my target equation. Because I've come to a point where adding these 3 equations has given me my target equation, I can now take their enthalpy changes and just simply add them. So the enthalpy change for my reaction here, remember we flipped this first one here, so the second one here, so it'll be negative 1411. That was negative, so it'll be plus 1560, and then minus 285.8. Once you find that, you have now found the enthalpy change for your reaction. All right, hopefully that helped.